Okay, we're going to talk about some equations that are related to planetary motion and satellites and things like that. So, you learned about Newton's law of universal gravitation and that the force of gravity between any two objects can be found by multiplying the universal gravitational constant by the mass of the first object times the mass of the second object divided by the distance between them squared. Okay, well, there are a couple of equations that are useful that can be derived from this. So the first equation is going to be for the orbital velocity of a satellite. Now, when I say satellite, I do not necessarily mean a communication satellite. So if this is the Earth, a satellite is any small object that orbits around a larger object. So, yes, a communications satellite would be a type of satellite. But the moon is also one of Earth's satellites because it's a small object or smaller object that is orbiting around the Earth. Okay, Earth would be a satellite of the sun. So just be aware that when we're talking about a satellite, it doesn't necessarily mean the technology satellite. Okay, so we have Newton's law of universal gravitation, which tells us the force of gravity between the moon and the Earth. But the moon is also in circular motion around the Earth. And so, remember, we know that the force, centripetal force, is equal to mass times centripetal acceleration, or v squared over r. Now, in the case of the Earth and the moon, or the Earth and its satellite, then the force that is holding a satellite in circular motion is the force of gravity. So the centripetal force is equal to the force of gravity, which means that we can set this g of m1, m2 over r squared equal to mv squared over r. Now, before we go any further, we need to think about what this stuff is. So if we call m1 the mass of the satellite, and we call m2 the mass of the planet, or the bigger object and the smaller object, then we've got g, the mass of the planet, times the mass of the satellite, divided by r squared. I know I just switched those, but it doesn't matter, is equal to, okay, this m here, when we think about circular motion, the mass that we're talking about is the mass of the moon going around. Okay, so this is going to be the mass of the satellite, the mass of the small object, times v squared. And we have these two r terms. So this r is the distance between the two objects, and this r is radius. But if you think about it, the distance between these two objects, the distance between their center of masses, is also the radius at which this moon is revolving in its circular motion around the center of its pathway. Okay, for the most part, it's a little wobbly, but which means that this r and this r mean the same thing. So we can still use the term r. Okay. Now, if we start rearranging this, what I'm coming to is the equation for velocity. So I'm going to try and get velocity by itself. So to do that, I'm going to cross multiply. So ms v squared r squared, I'm cross multiplying these guys, is equal to big G, mass of the planet, times the mass of the satellite, times r. And if I'm getting v by itself, then now I'm going to take v squared and I'm going to divide by the m and the r. And I'm going to get big G, mass of the planet, mass of the satellite, times r, divided by mass of the satellite, times r cubed. Oh, excuse me, r squared. Okay. Well, if you notice, the mass of the satellite cancels out, and one of these r's cancels out as well, leaving you with v squared is equal to big G, the mass of the planet, divided by r. Now, what we normally do for the mass of the planet or the mass of the large object is we use a capital M to indicate that. And if we're talking about the mass of the small object, we'd use a little m. And a lot of times, if you're specifying the radius of a particular planet, you'd use a capital R, as opposed to the radius that this is at. That would be little r, but the radius of the Earth would be big R. Okay, so knowing that, v squared is equal to big G, big M for the mass of the planet divided by R, and so V is equal to the square root of GM over R. This is your orbital velocity equation. And it's one to write down and remember. You're going to use that. And you're going to use this to find the orbital velocity of any object that is orbiting another object. Okay. The big thing to remember is that this is the central object, big M. It's not the small object or the orbiting object, which the orbiting object, the mass doesn't matter. Okay. You could also use this if you had the orbital velocity. You could use this to find the mass of the planet or to find the radius at which it orbits. All of that would be important. So another important concept is the idea of period. And I believe we've already talked about this, but if you have something that is in circular orbit, then if you think about if you're trying to find its velocity, then velocity is distance divided by time. Well, the distance around a circle is the circumference of the circle. And the time, so if we go around exactly one time, then that distance would be the circumference. And the time to go around one time would be the period. And period is a capital T, and period is just the time to go around one revolution. So exactly one time. So we can find the velocity that an object is orbiting at if we know the circumference of the circle, which is 2 pi r, and then the time that it takes to go around once. Okay, so this idea here, v is equal to 2 pi r over t. We also know that v is equal to the square root of gm over r. Okay, so if I have an object that's orbiting, then I can find its velocity if I know 2 pi r over t, but that same velocity would also be its orbital velocity, which is the square root of gm over r. And so I can set those two. And so I can set those two equal to each other. So 2 pi squared over t is equal to gm, and that's big M, over r square root. If I get rid of the square root, I'm going to square both sides, and that gives me 4 and that gives me 2 squared pi squared r squared over t squared. I just squared everything, which is equal to gm over r. This square just gets rid of the square root. Again, I'm going to cross multiply, and I get g big M t squared is equal, 2 squared is 4 pi squared r squared times r. This becomes r cubed. And if I'm looking for the period, t squared is equal to 4 pi squared r cubed over gm, and t is equal to the square root of 4 pi squared r cubed over gm. So this is your equation for the period of an orbit. But what also is important here is this right here. So 4 and pi are constants. Big G is a constant. And you can consider this mass of your large planet to be constant as well. And so you can see that t squared is proportional to r cubed. So essentially, the further away the object gets cubed is proportional to the square of the time it takes to go around. This is Kepler's third law. And Kepler's laws are the laws of planetary motion. We're not going to get into that in this class. If you take astronomy, you'll learn about Kepler's laws, I would assume. But this relationship here is Kepler's third law if you're interested. And this is our equation for the orbital period. So if you've watched the AP Daily video 3.4 video 1, then that video is going to get into the relationship between this equation for the force of gravity and this equation for the force of gravity, and specifically how you could find little g from this. So this may be a repeat if you've seen this, but essentially, since these are both equations for the force of gravity, then you can set them equal to each other. And I'm going to change this, and I'm going to use big M for the mass of the planet and little m for the mass of the object. And so M and M, those are the same. And this is over r squared. And again, you know that this is always talking about the mass of an object that is in the gravitational field of a larger object. And I would suggest that you watch this video because she's going to get into that concept. Well, if you look here, you've got little m and little m on both sides of the equation. And so when you're talking about the gravitational field strength or little g of the planet, you can see that that's not going to be affected by the mass of the little object. So the mass, or excuse me, the gravitational field strength of the Earth is affected by the mass of the Earth and how big the Earth is. The gravitational field strength of the Sun is affected by the mass of the Sun and the size or radius of the Sun. It's not affected by something that is getting pulled towards that large object. So the first thing, and again, she'll talk more about that, but little g can be calculated for any object by doing big G times the mass of that big object that you're trying to figure out the gravitational field strength for, divided by the radius squared of that particular object, or how far away the little object is from the center of mass of the planet, right? So if it's on the surface of the planet or the surface of the sun, then the radius would be the radius of that particular planet or that particular star. And that would give you the surface gravity. But if you wanted something like we were talking about, the gravitational field strength at the International Space Station, well, you could also calculate that in a different way. You calculate it with this if you know the mass of the Earth and then the radius that the International Space Station is above the center of the Earth. And you can calculate that gravitational field strength. The other thing I want to point out is that little g, since your mass of your planet and the radius of the planet aren't really changing, then this is a constant variable for the surface of the planet or the surface of the star or the surface of the object. If you are looking for the force of gravity of that object, then you're doing the mass of the object times little g. And we just said that little g was big G, big M, divided by r squared. And if we're multiplying it by little m, then we put that little m back in. And you can see, I just basically reversed what I did before. But you can see that when you do m times little g, which is this constant here, then you get back to Newton's law of gravitation, which is big G, big M, little m over r squared. Okay, that is all the derivations I'm going to go to. If you've made it this far, then I just want to point out on number 4, it talks about geosynchronous orbit. Geosynchronous orbit is when a satellite is orbiting above the same place. And so the period of the satellite or the moon or that type of satellite is the same as the period of the Earth or the planet or whatever. So here's another way to see that. You can see that where the red one is, it's always above the same place, and the yellow one is always above the same place. Okay, and they take the exact same time to make it around once as the Earth takes to make it around once. That's called geosynchronous orbit. Okay, so that's what it's talking about in number 4. Okay, geosynchronous orbit. The other thing I want to point out for number 4 is this is asking you to calculate the period. Don't just assume you know that the period of the Earth is 24 hours. You need to actually calculate that based upon the information and the equation for period to get the exact period of the Earth in seconds and in hours. And then again, number C here, or letter C, this word satellite don't be confused and think that we're talking specifically about a communication satellite that could give us information like what its speed was. We're talking about a satellite like a moon around a planet or a planet around a star. So we can use those satellites to determine the mass of an unknown planet. So again, if a moon was going around a planet, we could figure out the mass of the planet. And if a planet was going around a star, we can figure out the mass of the star based upon some stuff. So go ahead and look at your equations to see if you can figure that out. This link doesn't work, so. And then on number 5, you have 2 stars orbiting in a binary star system. So the thing you need to think about with number 5, particularly for the orbital speed of the star, they're both orbiting with centripetal motion, but the centripetal force, the radius there, a binary star system where both stars have the same mass, then they're basically the center of mass of the system is going to be halfway in between the 2 stars. And so think about that when you think about the centripetal motion of the objects. Okay, I believe with all of that, you should be able to do problem set 2 with those equations.